recording. All right, so we've got this situation, we've got this person who's trying to travel through all the cities, and the key thing that makes this the traveling salesperson problem as opposed to some other problem is you're starting at some city. Let's pick city 1 because that was where I saw the city first. They need to travel around to all of the other cities. They need to visit all of the other cities exactly once and then return home. Now this picture was just basically a random network that I put together for us, a random directed graph here with weights that I put together for us. Specifically, we're going to be looking at cases with our traveling salesperson problem where you don't have any missing connections between your cities, okay, or between your vertices. Now, the goal in terms of what we're trying to do here, we're trying to find that route where you start at one place, visit all the other vertices exactly once and return home. So note, this is totally defining a Hamilton circuit. And specifically, with these costs associated to traveling between the different vertices, we want to minimize that cost, and specifically, we want to minimize the costs across the entire route that we take, or the entire Hamilton circuit. And while we haven't done it yet, we will do this at the end of the example that we're working through. In order to find the cost of any Hamilton circuit that we're going to be dealing with, you simply add the cost associated with each of the directed edges or each of the edges involved in your Hamilton circuit. Okay. So the math we started in on last time, we said find that minimal cost Hamilton circuit, and we're looking on a complete directed graph, and we're always given the associated cost with each of the edges or each of the directed edges. Your book always gives it in terms of a matrix. Other books, depending on where you read this, will sometimes just give it to you in terms of the picture of the graph, or in some of them just in terms of a verbal description, which is always fun to deal with. Not that you can't, it's just you've got that one extra layer to put it into either your matrix or your graph. We said that we were going to be dealing with branch and bound method, which is systematically building up to all of the Hamilton circuits that are possible in the graph that we have. Hint, we're not really going to build to all of them. Instead, we're going to progress our way through a tree that would build all of the Hamilton circuits, but we're only going to build out that tree along the cheapest branches. Okay. Specifically, your book calls it a tree of choices. It's also known as a decision tree, where each of the vertices that we're going to reach would represent the Hamilton circuit partially made, and once we get to a leaf in that tree, that leaf would represent the Hamilton circuit that is now complete. In other words, we got back to our starting point. Okay? And we're going to keep track of the cost by that lower bound that we started dealing with last time. Okay? So I'm just going to walk through this example. So this is the exact same example that we had last time, and we're just going to finish off this example. So we started off and said that we had 4 cities. The costs associated with traveling between those cities are given by this cost matrix. This is the same matrix as before. By default, you label them 1 through whatever the last column is, and then those cities would be labeled like city 1, city 2, city 3, city 4, etc. Went ahead and we drew a picture representation of what that, and actually let me just make this so you can see both of them at once. We did a picture illustration of what this would look like, and I went ahead and did X1 through X4 to represent city 1 through city 4. I guess we didn't have to, it's just going to make it so we don't have to write as much in the future. Okay. The vertices here put the labels of the cities inside the vertices. That is, once you start getting into these more complicated graphs with tons more information on them, something that you'll often see with the labels of your vertices. Actually, some people do it all the time, we just haven't. Okay. And then put all of the associated costs on here. Notice one of the things we mentioned last time is these infinities are representing the connections that either do not exist or for whatever reason you're not going to take that edge. Okay. So for example, here in the position 1, 1, that's indicating that we don't have any loop here at city 1, meaning if you start at city 1, you're not going to return immediately to city 1 and just like, I don't know, take a highway loop around the city and come back home and claim you've done your job type thing. Okay. You're actually properly going to travel to another city. So we talked about that last time. The highlighted bit here was just an arbitrary Hamilton circuit, which we all agreed was a really terrible Hamilton circuit in terms of cost, because we could easily spot that there's probably another one that was cheaper in order to travel along. Okay. We did mention here, I don't think we actually counted it up, but if you did want to find the cost associated to this highlighted Hamilton circuit here, it would be 9 plus 6, so that's 15, plus 7 was at 22, plus 3 more, so that's 25. So just an arbitrary Hamilton circuit tells us that our cost is going to be 25 or less. Why 25 or less? Because we know for sure that we've got one of them with a cost of 25, so if we're looking for the minimal cost Hamilton circuit, it's got to be 25, this one, or we are hypothesizing that it's definitely going to be less. It's definitely going to be less, but actually a relatively large amount. Okay. All right, so we already talked about that. The only thing I didn't mention that we talked about last time is in the actual cost matrix, your Hamilton circuit will actually correspond to using exactly one of the elements per row per column, per row and column. Okay. And then we looked at lower bound. So lower bound was actually calculating it in terms of the matrix. And when we say lower bound, we're referring to the lower bound of the actual potential cost of the Hamilton circuit. So this is, we know for sure that any Hamilton circuit in this particular matrix can have a cost no less than whatever the original lower bound is. And as we progress through our decision tree, as we'll actually do today, we'll at each one of our internal vertices, and actually we'll get to leaves as well, but in each of the internal vertices, we'll adjust our lower bound to say, if you reach this vertex, then your Hamilton circuit has to have at least this cost, if not higher. Okay? And then when you get to the leaf, you'll get the lower bound will correspond to the actual cost associated with that Hamilton circuit. Okay? In terms of what we actually did, we took our same cost matrix that we originally had. We spotted all of the smallest entries in each row, and we did rows first, although you can flip-flop or rows versus columns. We wrote down what all those numbers were, and then we subtracted those lowest numbers from each row. Okay? And this was the adjusted matrix. We then also did the same thing with columns, although once we had subtracted everything from the rows, 3 out of our 4 columns already had a 0. The goal here is to get at least 1 0 per row per column. So the 4th column here did not have a 0, so we found our smallest number, which was 1, and we subtracted the 1 off of the column to get the new cost matrix that we're actually going to start with. The lower bound was then all of these numbers that we grabbed, all of our smallest numbers. We added them all up, and we said that the answer was 16 from last time. And this is roughly where we ended. The only thing that we progressed on further last time was dealing with what was going to be our strategy. So let's go over the strategy because we're about to use it. Okay. So our assumptions here is that we are going to start with city 1, so X1, and then we've got to figure out where we're going to go to next. So in terms of how to figure that out from your cost matrix, you look at the row associated with whatever city you're on. So if you're starting with city 1, we're going to look in row 1. You then look across row 1 and you find your smallest value. Hint, if you've already adjusted your cost matrix to grab your lower bound, you're going to have at least 1 0 per row, so spot your 0. If you have more than 1 0, like for example down here in row 3, your choice, you can pick either one you want. In our case, row 1 only has 1 0, so that means what we're going to do is we're going to actually say that after city 1, we're going to travel to city 2. We're then going to adjust this cost matrix appropriately, so that's going to be the first thing that we do today that's new. We're going to find the new associated lower bound with the adjusted matrix, and then we're going to do the same thing that says, all right, well, what if you didn't go to city 2? What if you went to one of the other cities? And then we'll do the same thing over there. Okay? So once you do this splitting, this branching effect right here, and notice it's 2 branches, so we're going to be building a binary tree for our decision tree. You've got the 1, which seems like the smart choice, and then the other one is all of the other things you could do. So it's literally going to be the smart choice we think we should do and everybody else. Okay? But this here, that's what we're going to be doing. So let me go ahead and rewrite this original guide because this was just directions. I'll rewrite this original guide, and what I'll do for each of the vertices in this decision tree that we're about to be building is inside of the vertex. I'll actually make these vertices obnoxiously large and box them, and inside the vertex I'll have both the current cost matrix as well as our lower bound and the scratch work that we're going to be dealing with. And I'm going to do that on purpose just so that the tree itself doesn't get so crazy, because I've done it otherwise and everybody's like, no, 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 no. That is too crazy to read. All right, so let us start here. So our cost matrix, so this is our, let me tag this. So this now is our decision tree. So starting from the root of this decision tree is going to be where our cost matrix is, infinity, 0, 6, 3. And we already started looking at what to do here. So this first little bit will be a slight repeat of the stuff that just barely got hidden right there. Okay, and I'm just copying down that cost matrix that we created at the end of last time, the one where we adjusted and got a lower bound of 16. So the lower bound here is 16. Okay, and according to this decision tree, the things that you know is we are assuming that we are starting our Hamilton circuit at city 1. Okay, so that's the root. That's the first vertex that we're dealing with. Now, there are two options that we're going to have, and I'm going to, on purpose, because this looks like a, we're going to be writing down sort of a piece of paper-esque here. I say esque because, well, it's not an actual piece of paper, it's the digital piece of paper. I'm going to make this binary tree in a way that we'll be able to see the whole thing. So I'm scooching this over so we have enough sides over here, space over there, excuse me. All right, go back to actually writing things. Okay. So the first thing that we do in this decision tree, as I can't apparently click the right buttons, is since we're starting here with city 1, we're going to look across row 1, we spot our 0, and that gives us our first real branch. So I'm going to go ahead and label this as 1, 2, 3, and 4. I'll do the same thing up here, and that'll tag which cities that we're looking at. So first child, what we want to do is we want to use from the cost matrix the position 1, 2 because it has a 0. And what that tells us in terms of the Hamilton circuit, that tells us we are going to select going to city 2 directly after leaving city 1. Okay. Now, the other option over here is we don't use C12. Okay. Before we go over to the, actually we could have probably do this one here first. No, let's do the one that actually makes sense first. So we'll do the one that we want to use first, and then we'll go over here next. So here's what you do. If you actually want to go ahead and use this guy, I'm going to go ahead and actually copy this matrix down exactly. And then we're going to adjust the matrix. So we have still infinity, 0, 6, 3. We have then, I'm going to put a hold right there, and we'll come back to it. Then we'll have infinity, we'll have 3, we'll have 1, we have 0, 1. Actually, let's go ahead and put in the 0, and I'll show you how to adjust. 0, infinity, 0. If I'm writing this out, if we're in class on either a chalkboard, well, a chalkboard you can erase, but if I use the .cam, which often happens in this class just to color code things, just because colored chalk is a pain in the butt to erase, you have to be really careful about what you write because pencil doesn't show up in the .cam and ink does, and I have to pay attention to that. The nice thing about this is I can actually erase. So, in terms of adjustments, here's what you do in this second guy. You actually now, we don't have to actually look at anything left in this node. The only thing we haven't dealt with yet is the lower bound. So I'm going to scooch this up so we have plenty of room to look at things. The things that we're going to look at is we'll need the 16 for the lower bound in just a second. And we're also going to need the fact that we're going here to city 2. Now, if we go to city 2, note what's going to happen. We're down here now at row 2 in terms of where we would want to progress to next. This is going to be our second vertex. We would be looking across the second row. Now, there's a couple problems when you look across this second row. As the matrix is written right now, notice in row 2, what do you have? You have this 0, which would naturally say, hey, let's go and grab that 0 because it's the lowest number in the row. But if you actually grab this 0, it's in the first column, which means your Hamilton circuit would progress as follows. It would go city 1, travel to city 2, travel back to city 1. Now, would that actually yield us a Hamilton circuit? What do you guys think? If we selected this guy, it would give us a circuit for sure, but would it give us a Hamilton circuit if we went city 1, city 2, and directly back to city 2? Turns out it wouldn't, because we wouldn't get to all of the cities. So one of the things that we do when we progress on to our next vertices is we need to adjust this matrix to make sure we don't accidentally pick up any subcircuits. Remember when we were building Hamilton circuits back in Chapter 2, and one of the things we had to watch out for was don't pick up little subcircuits before we get to all of the vertices? Same issue occurs here. So the first thing that we do is, because we don't want to go back to city 1 yet, what we do is we can't use C21. So what we do is we set position in the cost matrix or entry to 1 to infinity. So let me actually make that a different color to indicate that we actually adjusted it. So we adjust this to infinity so that we don't use it. Okay? Now, what's the problem? I shouldn't say that. Second thing that we need to worry about, and then we'll worry about adjusting. Second thing that we need to worry about is we also are never going to have this situation. So that's the first thing. Second thing is, are we ever going to be back where we have a situation that we're coming from city 1 and traveling to somewhere else? And the answer is no, because the first time we get back to city 1 is when we close our Hamilton circuit. Now, what that means, so this will never happen. What that means is, in terms of the cost matrix, everybody on the first row will never be used again. So we can set all of them equal to infinity, or as your book does it, he actually just deletes the row. I would actually recommend not following the pattern that your book shows of just removing this row from the matrix, because then you have to still keep track of, all right, which rows corresponding to which cities are left in the matrix, and that gets confusing really fast. What I would recommend is either making all of these infinities, which can get confusing really fast, or just do this adjustment. Put a line through the rows, meaning we're never going to use them again. Okay? I've done all 3 of those different methods in past classes, and the one that is definitely the easiest to see when you're first starting is by far just putting this line saying, nope, we're not going to use that row anymore. Okay? Turns out same thing occurs in one other situation, so this is the third adjustment. And there's always these 3 adjustments you have to worry about when you are building your Hamilton circuit. First one is the immediate close off. Do we have anything like that? The next one is a more general closing or getting a subcircuit before you want it. And the last one is also getting another subcircuit. So this next subcircuit is, can we ever have the situation where we're coming from a city and arriving at city 2 again? And the answer is, if we're currently at city 2, the only way to get back to city 2 from some future city, and this is probably the most important of all of these guys, is, well, you closed off some future subcircuit. So this is also a situation that you never want to have happen. So in order to tag that in our actual graph, not graph, we have in our matrix, any of the entries in the cost matrix in column 2 need to be set to infinity. Or if you prefer, it's perfectly fine to go ahead and just cross them off. Notice the entry that we used before, which was the entry 1, 2, that 0. That row and the column that that entry is in will always be crossed off, and then you'll typically have one more entry that needs to be converted to an infinity. Okay? At this point in time, we're then ready where we can do an adjustment on this matrix to get the new lower bound. Okay? Well, the current lower bound is 16. So to get the new lower bound, what we're going to do is adjust the current matrix with the top row and the second column out of play. We're going to adjust this new matrix with those 9 remaining entries to make sure everybody has a what? has a 0 in the row and the column. So if we look here, if we look at rows first, do we have any row that doesn't have a 0 in it? Yeah, so the row 2 here doesn't have a 0 in it, so you find your smallest value, and in this case, our smallest value is at 1. So here, we're going to adjust this guy by 1. Now, infinity, if we subtract 1 from infinity, no change. If you subtract 1 from 3, that guy will actually change to a 2. And if you subtract 1 from 1, well, that guy will change to the 0. Okay? Now, once we have this change of the 1 right here, do all of the other rows have a 0 in it? And hopefully you've all spotted yes. Now, check the columns. Do all of the columns that are currently in play have a 0 attached to them? Or in them, I guess I should say. It's not really attached. Do all of those remaining columns in play, so all the columns except for column 2, have a 0 in it? The answer is yes, which means there's no adjustment factor there for your lower bound. So this tells us in terms of our lower bound, we are going to add the adjustment that we just did to the lower bound that we came in with. So this means that the new lower bound associated with this particular matrix, or really this particular Hamilton circuit or partial Hamilton circuit, is going to be at least a cost of 17. Okay? Now, this is the way that we're going to progress every time we select a city that has the cheapest cost to get there, building from our current Hamilton circuit. And this will give you one branch of the 2 branches from each internal vertex. Okay? So this is one way. Let's go and pick up our other one that we skipped out on before. So that was where we selected using the highlighted entry. Now suppose we don't use that highlighted entry of the entry in the cost matrix of C12. What changes? Okay. Well, we're still going to have a cost matrix. So let me go ahead and copy down our cost matrix. So we'll have the infinity. We have the 0, the 6, the 3, the 0, the infinity, the 3, the 1, the 0, the 1, the infinity, the 0, the 5, the 3, the 0, the infinity. But in this case, if we're not going to use C12, what happens, we're going to set it equal to infinity. Why? Because we're not going to use it. So let me actually go back here and get rid of C12 and set it equal to infinity. So this is the change. That's actually the only change that you do for this matrix. Okay? The other one, we crossed off a row and a column to make sure we didn't go back and make any subcircuits here. We just make the one change of the entry that we're not going to use. Now, every time we're at any one of these vertices, we're going to go ahead and adjust to make sure we have a matrix that has a 0 in every row and every column. So looking at this new matrix, do we have a 0 in every row and column? Exactly. So we don't, so we have to do an adjustment. So just like before, sorry, I'm apparently starting to lose my voice, or at least having a frog in my throat right now. So we have an issue both at a row and at a column, so let's do the row first. It doesn't matter if you deal with the row first or the column first. You just have to pick one, and I would recommend if you pick row first, stick with it all the time. If you pick column first, stick with it all the time. Again, it doesn't matter which you pick. I choose row first. I think it was just because that's the way I learned the algorithm. But like I said, it doesn't matter. Okay. So if we look at our rows, the only row that doesn't have a 0 in it is that first row, and that's because we changed our 1, 0 to an infinity. So our smallest number here is a 3. So if we go ahead and adjust this row here by subtracting 3 from everybody, the first 2 entries stay the same because they're infinity. But the second 2 entries go down to what? You just subtract 3 from both the two entries, so the 6 will turn into a 3, and the 3 will turn into a 0. Now, when you're doing this on your own, you may actually want to erase the 6 and the 3 and put in the new 3 and 0. That way you don't have the scratch marks on here. I, on purpose, at least for these first ones, kept all the scratch work on here so you could see where the transitions were and color code them. In the future, if you guys want, we can totally go in, and for each of these guys, we can I can actually erase like the 6 and the 3 and put the 3 and the 0 in their places. Okay. So that takes care of our rows. You guys also said columns, so let's do a quick double check, make sure we didn't pick up any zeros that made looking at the columns not applicable. So we still have a 0, we still have a 0, we still have a 0, column 2, yep, we still need to deal with column 2. So if we deal with column 2, what's the smallest number in column 2? Hopefully you're all thinking the smallest number in column 2 is the 1 right here. So if we subtract 1 from column 2, subtract 1 from the 2 infinities, no change. But if we subtract 1 from the 1 and the 3, what happens? They'll both decrease by 1, so we'll get A, and just because it's difficult to write columns awesomely in types, we'll get 0, and we'll get 2. Do a quick double check, make sure I didn't mess up the arithmetic. Okay, so then the adjustments, all the adjustments that you actually had to make, in this case just the 3 and the 1, you would add to your lower bound from the parent vertex of where you're currently working, and you would then go ahead and add, when you add those two guys together, we'll get, in this particular case, what is that, 20? Is the new lower bound. Now, I'm going to zoom out. I'm going to realize that it may be difficult to see the individual numbers, but I wanted to give you the overarching strategy of what's going on here. Okay, so in terms of how we normally draw trees, we often draw the root at the very top and the guys branch out in either direction. I'm putting it in this sort of sideways way because we're going to hope to progress essentially straight down to get our Hamilton circuit, and these side ones are the other options. Okay, when you write this on your own, you can totally make it in a more triangular shape, however you want to. Okay, now in terms of once you get your two children vertices right here, the key thing is you look at the lower bounds. Okay, so if we go back in and highlight our lower bounds, we just got a lower bound of 20, and the previous child or the other child vertex had a lower bound of 17. Now remember what the lower bounds represented. They represented the current cost to travel along the Hamilton circuit created in however it was partially created to get to your current vertex. So any guesses which of these two vertices we should continue down? In other words, should we continue working from the vertex we just looked at, or should we look at the other child vertex? In other words, the one on the left or the one on the right? Left child, right child. What do you guys think? I would definitely recommend left child. You always look at where your lower bounds are. So like, for example, over here at this stage, once this matrix has been adjusted, you actually have two possibilities that you could use. You would go back and you'd say, all right, well, I would look, I'm still coming here from city 1. My 0 on the top row is now over here at city 4, and you'd have go to city 4, don't go to city 4. But there's no point of even looking at that over here because your lower bound is 20, which is higher than our lower bound of 16. So we're not even going to build out the decision tree in this level from this vertex right here until we reach a lower bound that is, say, 21 somewhere else, and that would then require us to go back to find the lowest lower bound that's currently in play. Okay? So in our case, grab the lower bound that's the lowest, so that would be this 17. So I'm going to go up and hide all of this. Note, when you're using one of these ones here where you didn't actually pick a vertex to go to, This one here is like restarting, so this would still be, you're looking at X1 goes somewhere. You're just not allowed to go to city 2. Okay. I don't think we ever need to come back to this one, actually, if I remember correctly. But let us go down to this next one. So this next vertex, the one with a lower bound of 17, we've got 2 options. Okay. So we've got the option where we don't pick the smartest path, or we have the option where we try to select the smartest path. Now notice where we're currently at in terms of our Hamilton circuit. So here with our Hamilton circuit, we've already chosen city 1 to city 2, and then we're going to try to select a new city, which means we're currently focused right here on our row 2, our 2 corresponding to city 2. So if you actually deleted the top row, just make sure you still label your rows according to the cities, same with the columns. So if we look across this row 2, you're looking for your zeros. If more than 1, you get to choose. If exactly 1, you're forced. So in our case, which city do we want to go to according to our cost matrix that we adjusted a little bit ago? Correct. We want to go to city 4. So this would represent, whoops, still highlighter. This would represent us going to X4 because X4 represented city 4. Now, what does that mean in terms of what we're selecting? That means we wanted to use C24 because that was the only entry in the second row of the cost matrix that was equal to 0. So then we repeat the process that we did in that parent vertex in this next level. So I'm going to copy down the matrix exactly. So we've got infinity, and we said these ones that we crossed off before actually needed to be infinities. So when I copy it down, I'm going to go ahead and just write them as infinities, but I'll also put a line through it so it's easy to see we're ignoring that row. The top row, all infinities, and I'm going to cross it off. Second row, we have infinity, infinity, 2, and 0. And it was the 0 guy that we were using. So let me actually go ahead and highlight that right here. That's the one that we were using. Make sure I stop highlighting. Third row down, we have 0. Second column all got converted to infinities. Then we have an infinity and a 0, and then a 5, infinity, 0, infinity. And we really crossed that guy out. Okay. So we'll go ahead and clean up this matrix. So we've got this guy. So there's 1, 2, 3, 4, and 1, 2, 3, 4. Now, using these same adjustments that we did in the last vertex, what happens? In order to not shut down any in order to not get back to a sub-circuit before you wanted to, in other words, not actually building your Hamilton circuit, we can't use C41. In other words, we're not allowed to have the next city we progress to after 4 to be back to 1. Why? Because that would mean we'd skip out on getting to city 2. We also can't get back to city 2, but we've already crossed those off, so we don't have to worry about those guys. Okay? So if we can't go back to city 1 from city 4, in other words, close off the circuit too early, we're going to go ahead and put an infinity right there. So let me make that a different color. So 4-1, where's 4-1? 4-1 is that guy. And we'll go ahead and make this a different color, and we used blue for our adjustments before. Now, the other thing that we're adjusting is when we went ahead here and got to city 4, there's from city 4, what's a good way to say this? We're never going to be able to arrive at city 4 from any other place. If you ever arrive at city 4 again, you would have created a little sub-circuit. So that means you're going to go ahead and cross off the row that corresponds to arriving, not row, the column that corresponds to arriving at 4, so that 4th column. You're also, notice we progressed from city 2 to city 4. Once we selected this guy right here of traveling city 2 to city 4, there's no other place that we're going to travel to from city 2. So we're going to go ahead and cross off all of that row right there of row 2. So it's probably easier, instead of trying to figure out which row and column you cross off at this level, just go back and box or circle in whichever entry you used to get to this current vertex, and just cross off the row and column that that entry is in. Okay. Now, that takes care of your adjusted matrix. The last thing that we do is we go and we look to see what we need to do in terms of our lower bound. In other words, we check to see if we have a 0 in every row and column, on purpose making this vertex a little bit smaller than the previous one. Okay, so what do you guys think? Do we need to adjust the matrix? Do we need to pull out any of the smallest elements, row or column, to make sure that we have zeros in all of our rows and columns? Or do we already have a 0 in every row and column? In other words, what's the lower bound, I guess I should say. Exactly. So in this particular case, we already have 0 in every row and column of those 4 entries that are still in play. This is a relatively small matrix. So here, we're only down to 4 entries left in play, but we have a 0 in every row and in every column, so no adjustments are needed in terms of dealing with your lower bound, which means the lower bound stays exactly the same as the node or the vertex above. Okay? So that's it in terms of the adjustments. Now, we still have the other option, back when we were coming up to this original vertex, or the parent vertex of the one we just did, and I realize that's a little bit tiny, so we're going to blow this up in just a second. So here our 2 options were, we were going to use the entry C24, or we weren't. So over here is don't use the entry C24. Okay? So that'll be the next one that we do. Did everybody write down what they wanted to for this vertex? Because I'm going to make it so you can't see it here in just a second. That is a good question. I always get that question at this stage. So this example, as well as a couple of our problems that will work in Chapter 4 for next week, if you do the full complete problem, it can take a long time. If you guys have looked ahead at the homework for this section, I think it's only 1 question, and that'll be plenty type thing. In terms of for a final exam, what I typically do would be something like do 1 branch or 1 level of this thing. So that would be like this stage right here, okay? Or something that is a really, really tiny tree. But that's one of the things that has to happen on our final exam, because we have a number of questions that are just, I mean, it could take you 1 hour to 2 hours to do one of the problems. So they get to be either really, really tiny examples, or more commonly, it only asks you to do 1 step of the problem, or it'll do some sort of analysis where I would show you this is the second to last step after somebody else solved it. What would you do to actually get the final answer? How would you interpret this? So yeah, there's definitely, if you wanted to solve this full problem, it wouldn't fit time-wise into the final exam unless I made it like 5 hours or something, which is not going to happen. Okay. All right. So I'm assuming, with that aside, that I've copied down everything that you need for that vertex. So let's blow this up and see what would happen if we don't use that element, that entry C24 in this vertex from the parent vertex of the one we just completed. So for this guy, here's what happens. First of all, I'm going to copy down this matrix exactly as it's written, and then we'll adjust it. So here we've got infinity. And remember, all the crossed off ones were the shortcut way of writing infinities. So the first row is all infinities. The second row is infinity, a second infinity, a 2, a 0. And then third row is 0, infinity, because it was under one of the lines. Infinity, that was trying to be an infinity. I realized it didn't quite work out. Then a 5, another infinity, a 0, and an infinity. Notice you don't have to put the lines to cross things out. You can just start blowing out infinities, and that works just fine. Some people love to do it. If you're coding this, this might be something that you really want to do. For our sanity together, I'm going to put the lines back in. Okay? So that's what we started with. Now, if we don't use the entry right here, this one that's highlighted of C24, what we're going to do is we're going to set C24 equal to infinity, because that's our tag of saying we're not going to use you. Okay? So let's get rid of 24, and we're going to write it with blue here to indicate that that's our change. Okay? Now, once you go ahead and have changed that one entry to infinity, we're then going to look at our lower bounds. Now, our lower bound here started at a 17. Okay? So we go back into our now adjusted matrix, and we look to see if we still have a 0 in every row and column. Well, we do have a 0 in every column, but do we have a 0 in every row? Correct. So you look back up at that row, and it looks like that's row 2 if we count the crossed off rows. So this one right here, where we adjusted our 0 into an infinity, it makes sense that we lost our 0, because originally we only had 1 0 on that row. If you originally had 2 zeros on the row, you might still have a 0 and no adjustment over here needed. But on this one, we need to adjust. So if we go and adjust that row 2, what's the smallest entry left in row 2? Yep, it is a 2, which means we'll go and we'll subtract 2 from every single entry on that row. And what happens then? Well, the infinities stay the same. Don't overthink it. But the 2 that's currently in there will change to a 0. Now that we've done that 0, or we have that 0, check, make sure we still have a 0 in every row and column, and we should, but let's double check just to make sure. And while you guys are double checking, I'm going to write the +2 on our lower bound. All right, so I'm seeing a 0 in every row and column still in play. So it looks like we're fine, which means what is our new lower bound for this matrix? Well, add the 2 to the 17 we had before, so that would be 19. Okay? Makes sense? Feeling kind of okay so far? Regardless of getting overwhelmed of how much potential work this could be, yes, that's true. But just in terms of the individual 2 branches, the left and the right branch that we do from each node, this is the same strategy each time. Now, next step is you look at your current leaves that are really going to turn into internal vertices, because we haven't completed any Hamilton circuits yet. But in this partially created decision tree, and I realize you probably can't read any of those numbers right now, we have what? We've got the root node up here. It had 2 children. We picked the leftmost child because it had a lower bound of 17, and we found its 2 children. The rightmost node had a lower bound of 20, so we didn't do anything. For our next iteration, you look at everybody who doesn't have any children currently written out in the decision tree, and you find the one with the lowest bound. This guy up here that you probably can't read has a lower bound of 20. The one we just dealt with has a lower bound of 19. And the one that we built just a second ago has a lower bound of 17. So any guesses which of those 3 vertices we're going to choose to find its children of? In other words, which of those 3 vertices we're going to choose to expand the algorithm on? Yep, it is totally the one with the lowest lower bound, which in our case is that lower bound of 17. So even though these 2 vertices right here, which you probably can't read other than seeing that we worked on them before, they have lower bounds, they totally both have children nodes or children vertices as well, we're not going to bother expanding them until they end up with the lowest lower bound in play. So since their lower bounds were 20 and 19, we currently have a lower bound of 17, which is even smaller. We're going to stick with the one that's at 17. Notice what happens is we are totally doing one of these things where we're essentially searching through this decision tree or building this decision tree in what is hopefully the most optimal way. So you're only going to bother doing the work while your lower bound is the lowest possible. But you do have to, once you select the vertex you're dealing with, deal with both of its children so you know there didn't happen to come up with a lower bound. Wow, that just doesn't feel right to say. A lower bound that's lower than the one you're currently working on. All right, so let's blow this up so we can see what's going on. So we go back to our work right here with the guy that had a lower bound of 17. Now, at this stage, where are we currently? So pull back the stuff we just had. Currently, we have built a Hamilton circuit that's going from city 1 to city 2 to city 4, which means our next one we need to select somebody going from city 4, which means we're going to be looking at our row 4. Now, if we look across row 4, we already have adjusted this matrix to ensure there's at least 1 0 per row and column. So we spot the 0, and here there's only 1. There's that guy right there. Note that doesn't really surprise you because here we're starting to get close to wrapping up this Hamilton circuit. I'm going to go ahead and do the full close-up to wrap this up, but you probably could figure out what the Hamilton circuit is right now. There's only one city left, and we just have to verify that we can get to that city and then back to the starting city. Okay. So in terms of the two decisions that we could make, we can either use, from the cost matrix, row 4, column 3, the guy that's the 0 that's highlighted, and that would give us a Hamilton circuit. It wouldn't yet, but it would give us close to the Hamilton circuit. So far, progressing through our Hamilton circuit is not what I just wrote. City 1, City 2, City 4, and then to City 3. We still have to ensure that we can get back to City 1. Okay? So that would be that way. The other option that we have is don't use that entry for 3. As that got a little bit scribbled. Sorry about that. I wasn't bracing my hand. Now, in terms of what we need to go to this next vertex, we know that we're coming from a matrix or coming from a earlier part of our Hamilton circuit with a lower bound of 17. So we're going to need to figure out what the new lower bound is. Okay? So first we'll copy down the matrix exactly. So we've got the first 2 rows are all infinities. And they'll also be crossed off. Third row is 0, 2 infinities, and an infinity at the end. Why an infinity at the end? Because it was a crossed off column. And the last row is infinity, infinity, 0, and infinity. Notice there's almost more infinities than to deal with, and this is why we're going to go back and cross off. First 2 rows were crossed off. Second and fourth columns are crossed off, so the only entries currently in play are down here in rows 3 and 4, columns 1 and 3. So let me go ahead and label these guys. When you get comfortable with this algorithm, or maybe even already, people don't always label the rows and columns. It's personal preference. Now, at this point, where would we go? Well, we know at this particular stage, what happens? We can't use what? Well, what's a good way to put this? Well, I just do it this way. We're going to eventually box this. Let's put in the scratch work. So we just selected this entry to use, which means what? It means automatically that in the future, you're never going to be going anywhere else from City 4, and you're also never going to be arriving at City 3 again. So this is where we cross off our third column for arriving at city 3 again, and cross off our fourth row for going somewhere else from city 4. So that makes sure that we don't have any more sub-circuits being created. Now, this matrix we're so close to the final answer that notice the only elements that got crossed off was the entry we just used. That one always gets crossed off. And then the two guys that were infinities that we already knew we weren't going to use. So in this case, when we crossed off the extra guys, it really didn't give us that much information. Okay. Now, in terms of calculating our lower bound, we start off with a lower bound of 17 from before, and we need to check to see if we need to adjust that lower bound. So looking at the entries still in play in this matrix, and I realize there's not many, do we have a 0 in every row and every column that's left in play for this matrix? Don't overthink it. Do we have a 0 in every row and column in play in this matrix? Yeah, there's literally one entry left and it's 0, so we're good, which means our lower bound stays at 17. Now, while you still have an entry left in play, that means you still have one more thing to do to create your Hamilton circuit this isn't yet a leaf of our decision tree. So we're still going to have two more things that we're going to need to worry about here if this one is still the appropriate lower bound to use. Okay. Now, I can tell you right now, since our lower bounds didn't change, here at 17, we're still the same as its parent vertex. If we go up and use this other branch here, there's no way your lower bound is going to be lower than 17. So you could just say, hey, because I know I can't be lower than 17, this is totally fine to go down here. However, proper procedure is go ahead and get both of them. This guy over here might have a lower bound that's still exactly 17, and you might want to actually progress along that way when you get down to the lower bounds of these next two children. Okay, so I'm going to go ahead and show you what's going to go on with this missing sibling of the guy we just created, but in reality, we're not going to use him. Okay, so if we go up here, what are we going to do? We're not going to use this highlighted guy, so we're not going to use entry 4-3 from our cost matrix. So if we start writing out our cost matrix, I'm just going to straight up copy what we currently have in the parent node right here, or this parent vertex. So first two rows are zeros, not zeros, are infinities because they're crossed off. Second column is crossed off. Fourth column is also crossed off. Okay. So now we just have four entries that are really in play. We have 0 and infinity. So the entries from row 3 don't change because we haven't mucked around with them. And then we have the entries from the fourth row. Okay. So that's the original thing that we have. Now, here's the deal. We're going to set the entry that we are not using to infinity. So this is entry 4-3 in the cost matrix, goes to infinity. So let's go ahead and actually do that. Now go ahead and choose here blue because that's what we've done for adjustments. Okay. Sorry about the infinity, it got a little wobbly. Now notice when we go back to try to find our lower bound, we look at our particular adjusted cost matrix and we say, all right, well, we need a 0 on every row and every column. So looking here with the 4 entries that are still in play in that matrix, do we have a 0 in every row and every column? And you only look at the non-crossed off entries. So we've had that in almost every case where we didn't use something. In fact, I think we did have it in every case that we've had it before. But the issue is, as one of you is asking here, is column 3 all infinity? And you could ask the same thing about row 4. Yes, you actually have a column as well as a row that's only infinities. Now, what's the problem with that? Infinity isn't a number. You can't go in and subtract off infinity off of one of your rows or one of your columns. It doesn't work because infinity was just our placeholder that said, I'm sorry, you can't use this entry. Well, if all of your entries here are infinities, what that actually means is the following. First of all, it means your lower bound doesn't really have a defined answer. And secondly, what it actually tells you is no solution. In other words, if you progress in this manner along your tree to get to that particular vertex of this decision tree, there's no way that you're actually going to be able to build a Hamilton circuit. It's not that this Hamilton circuit has too big of a cost. It's that there's no Hamilton circuit possible. Either you're going to get back to the starting point, the first city, too quickly, or you're going to close off a circuit, or if you put in all the infinities like what we did right here, you're going to get to the point where of the allowable edges that you can still use, there's none of them that'll take you to a circuit. Okay, so that's a way that you'll get a no circuit or a terminating path down the tree, if you will. Okay. I wanted to make sure to show you that because this doesn't have to happen just when you get really close to the end. Okay. Now, that then tells you definitely don't go down this branch. Okay. So going down to the child that we found, or the sibling to this guy that had no solution, so the one that had the lower bound of 17 that we were looking at before, we then have two choices. Okay? So with this guy with two choices, we have the standard choice, and actually let me make this arrow a little bit longer here. That didn't work well for me at all, did it? There we go. All right. What can we do? Well, when we look to see where we're going, currently we have the Hamilton circuit being made as city 1 to city 2 to city 4 to city 3. So we want to go somewhere else, and the place we want to go is where? Well, we only had 4 cities, so we want to come back to city 1. Okay. Well, the nice thing is, if we look up here in row 3, what happens? There's only one possibility that we're allowed to use. Luckily, it's a 0 because we made sure that happened before. So we're going to use here in the cost matrix C31, and we grabbed it because it was 0 and the only entry left. Okay. Now, the other option is don't use C31. And this time, let's actually do this one first. Notice what happens. If you don't use, I did not want to make that like that. If you don't use entry 3-1, your top 2 rows are already all infinities. And we'll go and put these guys as crossed off here. Your bottom row is also all infinities. And your last 3 columns are all infinities because they were crossed off. Now this guy that was a 0, if we're not going to use 3-1, what have we been doing? We've been setting that entry equal to infinity, which means this adjusted matrix is infinity. But what does that tell us about our lower bound? Or what does that tell us in general, I guess I should say? Again, don't overthink this one. We're at the tail end of completing our Hamilton circuit, so you can get some funky answers. But we're doing it on purpose because you can also get these type of answers earlier in your tree depending on what your graph originally looks like. Exactly. You can't get back to that first city. You can't get back to where you wanted to start at. So here, because of, again, the infinity, just like that last guy, you don't have a way to do a lower bound calculation. And in fact, if you ever get a row or a column of all infinities, this is when you get no solution. So if you do the proper, you switch up, you put the infinity in the appropriate little entry, you cross off the appropriate row or column, and you just go progress. If you ever get all infinities in either a row or all infinities in a column, that's when you've essentially boxed yourself into a corner. You can't create the Hamilton circuit, or you get this conclusion of no solution. Don't go along those lines. One of the things you can do is you can actually say that the lower bound there equals infinity if you want. I put the question marks because we were using infinity as a concept, but you can also put the lower bound as infinity there to indicate you can't do it. So that means we are currently operating in one direction left. So as long as this next thing keeps a lower bound that is less than 19, we don't have to pick up any of those hanging internal vertices that we left on earlier steps. Okay? So first thing that you do is what? You go and copy down the matrix exactly. So it'll be all infinities and then 1, 0. I suspect this is why your author of your textbook just deletes the row and the column. But if you ever wanted to actually implement this somewhere, I guess you could implement it with deleting rows and columns. But keeping track of the guys in terms of the rows and columns in an actual still the same size matrix as you started with sometimes is extraordinarily helpful in terms of keeping track of what you're doing so you don't have to relabel things at every single step. So we'll do the same adjustment that we've done before. So in terms of the adjustment, what would we do? We would box the answer or the entry that we used previously. We would then cross off all of the rows and columns that included that particular entry. Bam. What happened? In this particular entry right here, when we crossed off the row and column that the C31 was in, what happened to the entries in that matrix? There's not really a buzzword for it. It's more of a description. So what happened? In other words, are there any entries still in play? Are there any entries still in play in that matrix? What do you guys think? Yeah, don't overthink it. The answer there is a hard no. Why? Because every single one of them is crossed off by some line. Now, what does that mean? That means this is a node, not a node. This means that this is a leaf of your tree. This means we've actually reached a Hamilton circuit. Okay? Now, we still need to calculate the lower bound. Any guesses what the lower bound is for this, what's going to be a leaf of our decision tree? Don't overthink it. Remember, the lower bound is where you take all the smallest numbers left in the matrix after we adjusted and subtract as needed. There's no numbers left, so there's no adjustment possible here. So our lower bound is still 17. And remember, if we had zoomed out here to the entire decision tree, or at least the entirety of the decision tree that we actually calculated, what you'll find is actually, let me go ahead and do that. So we'll zoom to actually see this whole thing. Can we actually see the whole thing? Oh, I think that's a small, it's still letting me zoom tinier. All right, that's the whole thing. The only places where we could have still progressed were these top two, and I realize it's too tiny to actually see any of the numbers. But these top two internal vertices do still have children in the decision tree. No, we didn't actually go and find them because the lower bounds at these stages were 19 and 20. Well, 19 and 20 is still bigger than our current lower bound of 17, which means there was no reason for us to ever go back to these guys. Okay. Now, let's interpret what this means and blow it up so we can actually see the numbers. Okay. So we're down here and we reached a leaf of the actual decision tree. Our lower bound is the lowest lower bound that we got at any of our points. So what we say is conclusion. What does this mean? The actual Hamilton circuit itself, we actually tracked it as we went along. So this would be exactly go city 1 to city 2 to city 4 to city 3 and back to city 1. So that would be the actual Hamilton circuit. Now, the cost of that Hamilton circuit, actually, I probably don't need to put an equals for this one, would be how you got to each of these places. So we're going to be looking at, we went from city 1 to city 2, so we used C12. We went from city 2 to city 4, so that was C24. We went from city 4 to city 3, so that's C43. We went from city 3 to city 1, and notice that's C31. Notice these are exactly the C's with the appropriate subscripts that we used at each one of these branches. You can only see this last branch up here, but this last time we used the C31 position. Now, be careful. When you actually use these positions in the decision tree, all of them equaled 0 because we'd adjusted the original cost matrix. If you go back to the original cost matrix, so this is from original cost matrix. And this is where I really wish I had a copy of that original cost matrix right next to us. So let's find out where those guys are. I'm going to scroll back up to our original cost matrix, and what we're going to do is we're going to grab these numbers. Okay? So if we go back to the very, very original cost matrix, my sizing went all over the place. So we'll come up here. So in the original cost matrix, we are looking at, and I'm just going to underline them. We're looking at C12, so that was one we used. We're looking at C24, this was one we used. We looked at C43, we used that guy, and C31, we used this guy. Notice the underlined numbers right here. There is exactly 1 per column, 1 per row. That was something we had mentioned before, that a Hamilton circuit would do that. So your answers here would always be 1 per row, 1 per column in terms of the cost that you'd be using. We could also look at this in this particular graph down here. So maybe we use blue to indicate it. Here we said we went from 1 to 2. After 2, we went to 4. 4, we went to 3. And 3, we went back to 1. So notice it was actually the one that we picked before, but in the opposite direction. So that was totally coincidence at that point in time. Okay. So let us actually take these numbers of 3, 5, 5, and 4 back to where we're currently at. We're going to add them all up. Did not mean for that to be blown up that big. Sorry about that, guys. That's going to look crazy when I throw this into a PDF for you guys. So this turns out to be 3 plus 5 plus 4 plus 5. And notice that that answer is exactly 17. If you do your lower bound calculations correctly as you go through this decision tree, your lower bound will always be exactly that same cost. And you don't actually have to pull the extra work that we just did of pulling those individual cost values from the original cost matrix. Now, I purposed it for us today of doing that simply because I wanted to show you that the lower bound would always align with the sum of all the costs that you were going to be using on those edges. Okay, so that is the traveling salesperson problem. Every single one of them would be dealt with in the exact same way. If you have a really, really tiny situation like what you have with the example that we did here with only 4 cities in play, or 4 vertices in play of that original directed graph, it doesn't take too long. I mean, this still took a little while, but a lot of it was us actually talking about what to do at each section. If you knew exactly what to do at each decision, this wouldn't take nearly as long as what we actually did together. Okay, but that's really all you would do in these things, and this thing is something that is very automatable. Okay, so questions make sense in terms of what you would do at each stage to, in our case, adjust the matrix, because we did it all in the matrices. Basically, in terms of the not direction, so let me pull back up here and let me go back up to one where we actually still could have gone further, so maybe like this top one here. One of the things that can happen is often this, like you said, this not direction is very much the one that we pretty much think is a secondary choice. We're pretty sure that that's not the way to go. But what happens is maybe 2 levels down. So say this is larger than just 4 cities that you're dealing with. Maybe 2 levels down, instead of being 17 here, maybe the next one down turned up. So maybe this one was 17, but this next one down, maybe this one was 20. At that point, you have a choice. You could go back to this vertex that had a lower bound of 20, or you could keep progressing where you wanted to. But here's an even worse thing that could happen. Maybe you have the 17 here. Maybe you then at this next level have this 19 that we calculated. But maybe the child vertex of the vertex here with a lower bound of 17, maybe this one was 20. In that case, you come back to this 19 case, the lower bound of 19. So you have this sort of running collection of the lower bounds of vertices that still have children that you haven't calculated their children, and you sort of have them on a back burner. In this case, once we started going down the way that we wanted to choose of what we thought were the smart ways, it was such a small graph to start with that we were able to find our Hamilton circuit. There was no backtracking involved. But it does happen where you have to backtrack and go to select this spot over here where you didn't originally think that you were going to use that edge. So it's not always that there's more than one path with the same cost. Sometimes it's actually slightly different. More of you started off and close to your starting point, there was small values on your edges, and then as you got further on, the edge cost got larger. Other questions before we move on to talking about section 3.4? All right, I am not seeing any other questions come in, so let us look at section 3.4. So 3.4 deals with sorting algorithms, and I think I mentioned this earlier. You could totally do this. You could probably have a whole course almost just with dealing with sorting algorithms. So we're going to look at broad strokes, and then we're going to focus in on exactly 2 relatively straightforward sorting algorithms. I do have some extra resources that I'll go ahead and put up after class that you can look at some more different sorting algorithms as well. If you've ever dealt with sorting algorithms in the past, you've probably dealt with more than the 2 that we're just dealing with. Okay. So the first thing is talking about the order. And this is just a little bit of background. If you have some function g of n, when you label n, n often is referring to integers in this connotation. But if you have some function g, if it's considered order f, then there's some constant c such that the absolute value of your function g is less than or equal to the absolute, well, that constant, times the absolute value of f for all integers larger than some smallest value. Technically, you can do this for non-integers as well, but with the n there, it typically is dealing with integers. That being said, at this point, sometimes everybody has dealt with big O before or the order of a function before, and sometimes hasn't. So I don't know your guys' background at this point. If I say the order of something or big O of something in terms of this, are you comfortable with me saying that, or do you guys want some examples? I am perfectly happy to go either way. So you guys let me know. You guys want a couple of examples to see what's going on, or do you just, are you happy with knowing what that means? Okay. So let us look at a couple of examples then. Let me throw in some extra space. So all this means is it's depending on whether you're dealing with this in coding or in math, while it's roughly talking about the same thing, they're applied slightly different. So here is some examples. So suppose you have this function, n cubed minus 2n plus 17. I'm going to do a couple of different functions, and these are some common functions. Maybe you have natural log of n. maybe you have 2 to the n plus n squared, and maybe you have n times natural log of n. And that should be sufficient in terms of examples, and if not, you guys let me know. Okay. And let's go ahead and give ourselves a little bit more space so you guys don't see any of that other stuff yet. Okay. So one way to think about this, and this is very much the mathematical way of thinking about it, although it does correlate as well to what you would see if you're dealing with computers and optimizing code, which is often where it's used. What it's doing is it's essentially classifying you like a family. To some extent, you could think of it as dealing with these functions in terms of limits, if you will. Okay? So this first guy would be classified as order n squared. Okay? Now, why would that guy be classified as ordered n squared? Because this guy would fall under the family of polynomials that are degree 3 polynomials. Now, is this guy exactly the same as n cubed? No. Yeah, I meant cubed. Sorry, I think I said squared each of those times, didn't I? Pretend I said cubed and all that would make sense. Squared does not make sense. So let us put in a little bit of space here, and we'll see what it means in terms of this formal definition. So in terms of this formal definition, if we claim that n cubed minus 2n plus 17 is order n cubed, this guy would be the g function, and the n cubed would be the f function. So first you take the absolute value of n cubed minus 2n plus 17. And then you say, well, I can have an inequality. So what I'm going to do here is I'm going to say, you know what, this is the same thing almost as looking at each of these individual parts, well, individually. And I realize I don't need the absolute values around the 17, okay? But if this is a negative, if you switch it out so you take the absolute value of the individual terms, pluses, this thing could be identically the same or bigger depending on what the n is, okay? Now, and fix the typo. Apparently I really have squared on the brain. So next thing is in terms of this guy, I'm going to go ahead and say, hey, you know what, we've got here, this is the same thing as I'm going to keep the first term as an n cubed. But you know what, for the second term, this is the same thing. I can change that n into an n cubed, and what do we know? As long as you have a big enough value for n is smaller than n cubed. Okay? So I just swapped this n with an n cubed. Now for this last one here, there's no n's whatsoever. So I'm going to claim I'm going to swap out the 17 with an n cubed. That's definitely way bigger than just a plain old 17. Now, this is something you can actually add together. So we've got what? That looks like 20 of them. 20 times n cubed. Yep, there's absolute values around all of this stuff. That's what makes it work. So this would tell us here that the polynomial n cubed minus 2n plus 17, since it's less than or equal to 20 times the absolute value of n cubed, this guy would be order n cubed, and in this particular case, that capital C, that constant, is 20. What it means is, in practice, when you have some sort of function, you're looking at the type of function it is. So if you look at this in terms of limits, your n cubed with other stuff at the end, or your just plain old n cubed, are going to act the same way. In terms of coding, it's going to tell you how quickly your algorithms are going to compute. So something that is a polynomial in terms of an n cubed time is going to take longer to compute. If it was simply order n squared, that would be a polynomial where the highest term is an n squared term. Okay? And that extrapolates out to other types of functions as well. If we come down here to the next example, this guy, this one is order log n, or as what you often see, log base 2n, or the other way that you can see that is log n. Realize I normally do the one right here where it says base 2, but that's the shortcut way of saying base 2. And these two are exactly the same in terms of the order, simply because of change of base formulas. This one down here is a combination of an exponential form and an n squared term. If you only had the n squared, this would be order n squared, a polynomial order. This one here, if you only had the 2 to the n, it would be an exponential order, or order of 2 to the n. Any guesses of which of those is going to get bigger faster? Feel free to think back to limits. That's sometimes one of the best ways to tell who's going to grow quicker. It turns out your exponentials grow quicker. So this guy, you could technically say it's order 2n plus n squared, but we don't. We would say it is instead just order 2n because the 2n part in terms of the limits would be so significantly larger it would beat out the n squared. Okay? So to some extent, this is saying what's a good way of saying this, that these functions are, we don't care about the nitty-gritty details, but overall what classification, what family of functions do they live in. Okay? In this last one here, this guy is actually would be order n log n, or if you prefer, n log base 2n. Math, we a lot do natural log is our sort of default log. With computer science, you often have a default log of log base 2. Again, it depends on what you need. But one of the reasons of writing that one out in terms of sizing, if you have something like order n, and I'm going to put these as inequalities, but the symbol's a little bit off here. If you have a function that's order n log n, that's a function that's bigger. I'm putting quotes around bigger even though you can't see it. And bigger still would be if you have order n squared. And you can keep going. And so it's a way of categorizing your functions and sizing. Okay. Now, how we're going to use it in this sense is we're going to look to see how efficient our sorting algorithms are. Like I said, we're only going to focus in on 2 of them, and one of them is going to be one of the most inefficient guys. It's actually going to turn out to be order n squared. And in terms of the other one that we're looking at, we're actually going to look at somebody who's going to be one of the more efficient, so one of the quicker algorithms, and it's actually going to turn out to be order n log n. Okay, so that's the background. That's as much as you actually need for what we're going to be doing in our class. So in terms of the things that we're going to be looking at in this section, we're going to be looking at sorting algorithms. These sorting algorithms use binary search trees. So what we've looked at in the previous couple sections was searching through our binary trees, comparing 2 items at a time and keep going. So it's actually really similar to that decision tree that we made for our traveling salesman problem. Okay? Now, fair warning, if you are actually sorting a grand total of n items, what happens is, one thing, you have for the tree that you build, you'll have a grand total of n vertices, but it turns out that this guy has at least n factorial leaves, so it can get really large. And the other thing that happens is the height of this binary tree is going to be greater than, technically speaking, it's the ceiling of log base 2 of n factorial. Nobody actually wants to compute that. Well, okay, some people did. And what they found was that expression of the ceiling of log base 2 of n factorial was actually, and this is where the order comes in, an order of n log n. And the base 2 came out because of the base 2. And remember, when we had our height formulas for binary trees, the subscript here indicated the binary tree because there were 2 children at each node, or 2 children at each vertex. Okay. Now, this gets us to our theorem. It's the main theorem of this section, which talks about if you're dealing with some sort of sorting algorithms and you're comparing 2 things at a time. In other words, you're building a binary search tree. The number of comparisons that you're going to need to sort those n items is going to be at least this order of n log n, okay? And that's where these 2 guys tie in together, okay? So that's the background. The only other thing in this section that we're going to cover are 2 types of sorting algorithms. Okay. And the first one is sometimes people's favorite, bubble sort, okay? So in terms of bubble sort, this one is, well, there's pros and cons to all of these guys. So let me first show you what the algorithm is, and then we'll talk about pros and cons, although based on the number of time, we'll have to finish up this example next time. So here's the idea. You're given some sort of sequence of your n objects in whatever randomized order they're currently in, okay? You walk through the sequence sequentially, and if the smaller item is first, you swap them, and you keep going, okay? And you keep going until you get one entire pass through your sequence where you haven't had to do any flipping whatsoever. In other words, you haven't had to do any swapping whatsoever. So the goal here is you want to get these guys ordered so that you've got whatever the first subscript is. So I'm going to put question marks for the subscripts so that you actually have this thing going on at the end. Okay? In other words, they're all in sequential order. Now, in terms of how many total swaps that you're going to have to do, I shouldn't say swaps, the maximum number of passes through the sequence that you'll have to worry about is n minus 1 passes through the sequence. And it turns out that this guy is actually order n squared. Okay. Now, let me show you an animation of this guy. I'm so glad I have this prepped up now. So this is an animation specifically of bubble sort. It is not in any way, shape, or form a very nicely colored bells and whistle ones, but it does show you exactly what's going on in the bubble sort without me having to write it all out. Okay. So I'll share this link with you guys if you want to play around with it on your own. So here you've got some sort of randomized sequence of numbers. So this is your random sequence. What would bubble sort do? The first thing it would do is it would take on your first two numbers and it would swap them to make sure the lowest one is first. Next thing it would do is it would move, and these two guys are already in order, so no change. Next thing it would do, no change because the smaller one's first. Swap it if the smaller one's not first. And notice it keeps on going every time. It swaps only if the smaller one is not first. In other words, the larger number is coming before the smaller number. Okay? Notice what's naturally occurring here with your bubble sort, and that's just one pass. Okay? That largest number of 80, which was originally somewhere over here, got pushed all the way to the end. So when we go through the next iteration, it starts again. And what happens? These first ones were already in order, but then the next time that it has somebody out of place, in other words, a larger one first, it'll swap it, and then it keeps on going. Those two are in order. But here with the 70, it's going to pick up the 70, and notice every time 70 is larger than somebody, it's going to get swapped. Here, 74 was bigger. Notice 74 right here is the biggest number for a little while, so notice that 74 is going to get carried along until it gets to its final position right there. And notice once we've got these guys set in their final position, you're never going to have to change once the highest numbers are over in their furthest position. And you keep on going. Notice in a randomized sequence, this guy is not the most efficient. It's actually one of the most inefficient, unless for the ones that have actually been specifically calculated to be as inefficient as humanly possible, not sort of naturally made sorting algorithms. Okay, this one is an ordered n squared. Okay? So what we'll talk about next time is we'll talk about this guy a little bit more, and then we'll go on to talking about the next sorting guy, which is much more inefficient, which is called merge sort. But what I'll do for you is I've actually got a couple of different animations that visually show what's going on with these sorting algorithms, and I'll make them visible for you guys right after class. There's one of them that totally should have a warning if you have seizures on it, just because they color code it with flashing colors because they speed up the swaps and the sorting mechanism really, really fast. But I'll post all those for you guys so you can look over them. But next time at the beginning of class, we'll finish up this section, which is the last section in Chapter 3, and then we'll move on to the beginning sections of Chapter 4. Okay? So that is it for today. I don't have anything else for